All right, welcome back everyone to the deep dive. As always, we try to cover some of the latest and greatest in machine learning research. And today, we're diving into a paper that just might make a splash, so to speak.
Oh, splash. I like that. All right, I'm intrigued.
Yeah, so it's all about making probabilistic inference more efficient, really speeding things up.
Okay, now that's a challenge I can get behind. Probabilistic inference, it's the heart of so many AI applications, and it's computationally heavy, to say the least.
Yeah, you're absolutely right. So the paper we're looking at is called Combining Local Symmetry Exploitation and Reinforcement Learning for Optimized Probabilistic Inference.
Okay, so right off the bat, it sounds like they're bringing together a couple of really interesting ideas. Symmetry exploitation, that's all about finding and using those inherent patterns and structures in the data. And then we've got reinforcement learning, that's the AI that's been making waves and game playing and all sorts of other optimization tasks.
Exactly. So before we get too deep into the nuts and bolts of the paper itself, let's take a step back and talk about why this problem of efficient probabilistic inference is such a big deal. Why should our listeners care about this,
Well, think about it this way. Whenever an AI system has to make a decision under uncertainty, it needs to reason about probabilities. What's the most likely outcome? Or what's the distribution of possible outcomes? And this kind of reasoning is fundamental in fields like computer vision, robotics, natural language processing, really all over AI.
Right. So when a self-driving car is trying to figure out what those objects are around it based on its sensor data, it's using probabilistic inference. Or when a robot is planning a path to avoid obstacles, it has to reason about the probabilities of different movements being successful.
Exactly. And in natural language processing, probabilistic models are used for everything from predicting the next word in a sentence to understanding the sentiment behind a piece of text.
So the more complex these AI systems get, the more variables they have to deal with. And the relationships between those variables can be pretty intricate.
Yeah, and that's where probabilistic graphical models come in. They provide a really elegant way to represent these complex dependencies between variables.
So these graphical models, they're basically visual representations, right? You've got nodes that represent variables and then edges that connect them, showing how they influence each other.
Yeah, exactly. And one of the most common types of graphical models is a factor graph, where you have these factors, which are basically functions that capture the relationships between a subset of the variables.
So you use these graphical models to kind of map out the whole probabilistic landscape of your problem, so to speak.
Precisely. But here's the catch. Even though these graphical models give you a really nice way to represent these complex probability distributions, actually performing inference on them can be computationally very expensive.
Okay, so what do we mean by inference in this context? What's actually happening when we do inference?
Well, imagine you're trying to figure out the probability of a certain event happening, given some evidence that you have. What's the probability that it's going to rain tomorrow, given that the sky is cloudy today? To answer that, you'd use your graphical model to essentially combine the information from your evidence with the underlying probabilities represented in the model to come up with a new updated probability.
Okay, so it's you're taking what you know and then using the model to sort of propagate that information through the network of relationships to get an answer.
That's a good way to put it. And one of the key algorithms for doing this kind of probabilistic inference is called variable elimination.
Now that rings a bell. I remember encountering that in a machine learning course I took a while back.
Yeah, it's a pretty fundamental technique. The basic idea is you start with your factor graph, and then you systematically eliminate variables one by summing out their influence on the other variables.
Okay, so summing out a variable, that sounds kind of abstract. What does that actually mean in practice?
Well, imagine you have a factor that involves 3 variables, let's say A, B, and C, and you want to eliminate variable C. So what you do is you essentially create a new factor that involves only A and B, and you do this by summing over all the possible values that C could take on, weighted by their respective probabilities.
Okay, I kind of get it. So if C could be either 0 or 1, you'd calculate the new factor for A and B by first setting C to 0, calculating the probability, then setting C to 1, calculating the probability, and then adding those two probabilities together.
Exactly. And you repeat this process for all the factors that involve C. So you've essentially marginalized out the influence of C, and now you're left with a simplified model that only involves A and B.
Okay, so it's you're collapsing the model down step by step until you're left with just the variables you're interested in.
That's the idea. But here's the tricky part. The order in which you eliminate these variables can have a huge impact on the computational cost of the whole process.
Oh, really? Like some orders are much more efficient than others.
Exactly. So if you choose a bad elimination order, you might end up creating these intermediate factors that are just massive. They involve a ton of variables, and the computational cost of dealing with them just explodes.
Okay, so I'm guessing that finding the optimal elimination order, the one that minimizes the cost, is not exactly a walk in the park.
You got it. In fact, as the authors of this paper point out, it's what's known as an NP-hard problem.
Yeah, NP-hard. Those are the computational problems that just love to make our lives difficult. As the problem size grows, the time it takes to find the absolute best solution just blows up exponentially.
Right. So in practice, people have often relied on heuristics for finding decent elimination orders. These are kind of like rules of thumb. They often work pretty well, but they don't guarantee that you'll find the most efficient solution.
So it sounds like this paper is trying to come up with a smarter way to find those good elimination orders.
Exactly. And they do that by drawing inspiration from another area of machine learning that's been grappling with similar complexity challenges: tensor networks.
Okay, tensor networks. Now, those are becoming increasingly popular, especially in areas like quantum physics and deep learning.
Right. And just like probabilistic graphical models, tensor networks are all about representing complex relationships. But they use this different mathematical framework based on tensors, which you can think of as multidimensional arrays.
All right, so they're kind of like matrices, but they can have more than just rows and columns, right?
Exactly. And the key operation in tensor networks is tensor contraction, which is kind of analogous to summing out a variable in a graphical model. You're essentially combining the information from different tensors to get a new tensor.
Okay, so I'm starting to see the connection here. Both probabilistic graphical models and tensor networks are dealing with this challenge of efficiently performing operations on these complex, interconnected structures.
Exactly. And what's really cool is that researchers in the tensor network world have had some success using reinforcement learning to find really good contraction orders. So the authors of this paper thought, hey, why not try adapting those techniques to the problem of variable elimination in graphical models?
So they're kind of borrowing a page from the tensor network playbook.
Precisely. And that's where the first part of their paper's title comes in: combining local symmetry exploitation and reinforcement learning. They're using RL, reinforcement learning, to guide the search for good elimination orders, just like it's been used in tensor networks.
But I'm guessing there's a bit more to it than just applying RL directly.
Yeah.
What's this local symmetry exploitation all about?
That's the really clever part. So often in these graphical models, you have groups of variables that are, in a sense, interchangeable.
Okay, interchangeable. So like if you swap their values around within a certain part of the model, it doesn't really change anything fundamental about the probabilities.
That's exactly it. Think of it like if you're modeling a system with multiple identical sensors. The readings from each sensor might be different, but their role in the overall system is essentially the same.
So they're symmetric in how they contribute to the overall picture.
Exactly. And the traditional way that RL has been applied to this kind of problem, finding good elimination orders, it typically just looks at the computational cost based on the raw size of those intermediate factors we talked about earlier.
Okay, so like if an elimination step looks like it's going to create a really huge intermediate factor, the RL agent might shy away from it, even if that big factor actually has some hidden symmetry that could be exploited later to simplify things down the line.
Yeah, that's a good way to think about it. And that's where this local symmetry exploitation comes in. This paper introduces a new way for the RL agent to assess the cost of an operation.
Okay, so instead of just looking at the size of the intermediate factor, it's taking into account the potential for representing that information in a much more compact way by making use of these local symmetries.
Exactly. So imagine you have a bag of, let's say, 100 red marbles. Instead of listing each individual marble, you can just say, hey, I've got 100 red marbles. That's kind of the essence of how exploiting symmetry allows you to create a more compact encoding.
Okay, so that makes sense. You're capturing the essential information without getting bogged down in the unnecessary details.
Right. And by making the RL agent aware of these symmetries and how they can lead to these more efficient, compact representations, it can then start to explore elimination orders that might have seemed way too computationally expensive under the traditional way of measuring cost.
So it's like it opens up a whole new set of possibilities for the RL agent to find those clever, efficient solutions.
Exactly. And the potential benefits here are pretty huge. Faster and more scalable probabilistic inference means you can tackle much more complex AI problems. You can build models with way more variables, and you can reason about more intricate relationships without hitting those computational walls.
Okay, so this could have a pretty big impact on the kinds of AI systems we can build in the future.
It definitely could. And for the listener who's really interested in the details of how they pull this off, let's dive into the structure of the paper itself.
All right, let's do it. I'm ready to get into the nitty-gritty.
So they start by laying the groundwork. They define what probabilistic graphical models are, what factor graphs are, how variable elimination works. They clearly lay out the challenge, which is that while variable elimination is a fundamental technique, its efficiency really hinges on the order in which you eliminate those variables, and finding the optimal order is a tough computational nut to crack.
Okay, so they're setting the stage, making sure everyone's on the same page before they introduce their new approach.
Right. And then they make that crucial connection to the world of tensor networks. They formally establish this duality, this kind of mathematical correspondence between probabilistic graphical models and tensor networks.
Okay, so they're showing how the concepts and operations in one domain map onto the concepts and operations in the other domain.
Exactly. So you can think of a random variable in a PGM as being analogous to an index in a tensor network, and a factor in a PGM is kind of like a tensor in a TN. And the operation of summing out a variable during inference is similar to contracting an index in a tensor network.
Okay, so this mapping gives them the justification for borrowing those RL techniques from the tensor network world and applying them to the problem of variable elimination.
Right. But they also point out that the mapping isn't always perfectly one-to-one. In typical tensor networks, an index usually connects at most two tensors, whereas a single random variable in a factor graph can be involved in multiple factors. So while the basic principles are the same, there are some subtle differences to keep in mind.
Okay, that makes sense. It's like the core ideas transfer over, but you have to be mindful of the specific nuances of each domain.
Exactly. Now, once they've established this connection, they go on to formally reframe the problem of finding an optimal elimination order as what's called a Markov decision process, or an MDP.
Okay, an MDP. Now, that's a concept I've come across in reinforcement learning before. It's essentially a way to model a decision-making process where the outcome of each decision is partly random.
Right. So you can think of it like this. The current state of the problem is the factor graph you're working with. The possible actions you can take are the different choices of which variable to eliminate next. And the reward you get, or, well, in this case, it's more like a penalty, depends on the size of the intermediate factor that gets created after you eliminate that variable.
Okay, so the RL agent's goal is to learn a strategy, a policy, for picking which variable to eliminate at each step so that it minimizes the overall cost or penalty over the entire inference process.
Exactly. And they even suggest that a graph neural network could be used to help the RL agent make these decisions, because graph neural networks are really good at dealing with these kinds of graph structured data.
All right, so they're bringing in all these different tools from the RL toolbox to tackle this problem.
They are. And now here comes the heart of their contribution. How they incorporate this idea of exploiting local symmetries into this whole RL framework.
Okay, so let's get into the details of that. How do they actually do it?
Well, first, they give a very precise definition of what it means for a factor within the graphical model to exhibit these local symmetries. Essentially, it means that there are certain sets of random variables within that factor that are interchangeable. If you were to permute or swap the values of those variables, the resulting probability, or what they call the potential of that factor, wouldn't change.
Okay, so they're formalizing this notion of interchangeability, making it mathematically precise.
Exactly. And they give a clear example of a symmetric factor where if you were to swap the values of these interchangeable variables, the potential of that factor would remain exactly the same.
Okay, so they're showing that these symmetries do actually exist in real-world graphical models.
Right. Now, once they've defined these symmetries, they introduce the concept of what they call symmetric random variables, or SRVs.
Okay, SRVs. So these are variables that are part of these symmetric groups, right?
Exactly. And the key insight here is that you can represent these symmetric factors in a much more compact way by using what they call histograms.
Ah, histograms. Those are those bar charts that show the frequency of different values, right?
That's it. So instead of needing to store the potential for every single possible combination of values of the original variables, you just keep track of how many variables within the symmetric group take on each possible value.
Okay, so instead of saying variable A is 0, variable B is 1, variable C is 0, you just say two variables are 0 and one variable is 1.
Precisely. And this can lead to a really significant reduction in the amount of information you need to store and process.
All right, so that's how they're exploiting the symmetry to create those more compact representations.
Exactly. And one of the key theoretical results of their paper, which they call Theorem 5.1, really highlights the power of this approach.
Okay, Theorem 5.1, what does that tell us?
Well, it basically proves that when you perform the operation of summing out a symmetric random variable from a factor that has these symmetries, the resulting factor, the one you get after you eliminate that variable, it will also retain certain symmetries.
So the symmetry kind of propagates through the elimination process.
Precisely. And this is important because it means that you can perform the sum out operation directly on the compact histogram-based representation of the factor.
Okay, so you don't have to go back to the full, potentially massive, unsymmetrical representation. You can just work with the compact one the whole time.
Exactly, and that saves a ton of computation. Now, they also have another theorem, Theorem 5.2, which deals with what happens when you multiply two factors that have symmetries.
So that's like the other fundamental operation in variable elimination, right? You sum out variables and you multiply factors.
Right. And this theorem basically describes how the symmetries of the two factors combine when you multiply them. It's a bit technical, but the key takeaway is that the resulting product factor will also have certain symmetries that you can exploit.
Okay, so they're showing that these symmetries are preserved under the operations that are used in variable elimination.
Exactly. And this allows their RL agent to reason about and exploit those symmetries throughout the entire inference process.
So it's like the RL agent is not just looking at the problem myopically, one step at a time. It's taking into account how its decisions will affect the symmetries and the computational cost down the line.
Right. Now, to really show that their approach works, they present some experimental results.
Okay, let's talk about those experiments. What did they find?
Well, they compared their method, the one that uses RL and symmetry exploitation, to some of the more traditional methods for finding elimination orders.
So how did it stack up?
It performed really well. They showed that by actively exploiting these local symmetries, they were able to achieve a significant reduction in the total size of the intermediate factors generated during variable elimination.
Okay, so they were able to make the whole inference process much more efficient.
Exactly. And importantly, they showed that their approach never actually makes things worse. Even if there are no symmetries to exploit, it doesn't add any extra computational overhead.
So it's always a win-win. Either it finds some symmetries to exploit and makes things more efficient, or it doesn't. And it just performs as well as the traditional methods.
That's a good way to put it. So the experimental results really provide strong evidence that this approach has a lot of potential.
Now, before we move on to our novel notions segment, I think it would be helpful to put this work into a bit of historical context.
Yeah, that's a good idea. So probabilistic graphical models, they've been around for quite a while, since at least the mid-1990s.
Okay, so they're not exactly a brand new concept.
Not at all. And variable elimination, that's one of the classic algorithms for doing inference in these models. It was developed back in the mid-90s as well. And researchers realized pretty early on that finding the optimal elimination order is really hard. It's that NP hard problem we talked about.
So that led to the development of all sorts of heuristic methods for finding good, but not necessarily optimal elimination orders.
Exactly. Now, this idea of using RL to optimize things in graphical models, that's a more recent development, and it's really been driven by the huge progress that's been made in RL over the past decade or so.
Right. RL has really taken off, especially with all of the successes in game playing and robotics.
Yeah. And this paper, it really builds on that success and applies it to this new domain.
Okay, so it's kind of like they're standing on the shoulders of giants.
That's a good way to put it. And this work also fits into a broader trend in machine learning research that's all about developing more efficient probabilistic inference methods by taking advantage of the structure that's present in the data and the models.
Okay, so they're not the only ones who are trying to make probabilistic inference faster and more scalable.
Not at all. There's a whole community of researchers working on this. And they're exploring all sorts of different approaches, like exploiting global symmetries, using tensor decompositions, leveraging causal relationships, and even using ideas from quantum computing.
Wow, so there's a lot of really interesting research happening in this area.
There is. And this paper, it's definitely a valuable contribution to that effort.
All right, so let's do a quick recap of the key takeaways from this paper just to make sure everyone's following along.
Sounds good. So the main takeaway is that finding an efficient order of computation is absolutely crucial if you want to scale probabilistic inference to larger and more complex AI models. And RL offers a really powerful data-driven way to learn good computational strategies.
And the key innovation here is that by specifically looking for and exploiting these local symmetries that are often present in the data, we can drastically reduce the computational complexity of the inference process.
Exactly. And by changing the way the RL agent evaluates the cost of its actions, to take into account these symmetries, it can discover much more optimal solutions than it could with traditional methods.
So this has the potential to really unlock a whole new level of complexity in the kinds of AI systems we can build.
It really does. Now, let's shift gears a bit and move on to our novel notions segment, where we like to speculate about where this research could lead next.
All right. I always enjoy this part. So what are your thoughts? What are some interesting directions that future research could explore, building on the ideas in this paper?
Well, one thing that really struck me is that this paper focuses on static probabilistic graphical models. Models where the structure and the probabilities don't change over time. But what if we were to apply these ideas to dynamic graphical models?
Oh, dynamic graphical models. Those are models that evolve over time, right? Like as new data comes in, the structure of the model might change or the probabilities might get updated.
Exactly. So think about things like hidden Markov models or Kalman filters. These are used all the time in areas like speech recognition, time series analysis, robotics, all sorts of things.
Yeah, okay. So how could we apply the ideas from this paper to those kinds of models?
Well, that's a great question. Could we train an RL agent to not only find a good elimination order at each time step, as the model is evolving, but also to adapt its strategy on the fly based on how the symmetries within the model are changing?
That's an intriguing thought. Like imagine a system that's tracking multiple interacting objects. The symmetries between those objects might change over time, depending on how they interact with each other. So the RL agent would need to be able to detect those changes and adjust its elimination order accordingly.
Exactly. And you might even need to modify the RL agent's cost function so that it takes into account not only the computational cost of the elimination order, but also the computational cost of detecting and exploiting those changing symmetries.
Yeah, because if it takes too long to figure out what the symmetries are, then you might lose all the efficiency gains you were hoping for.
Right. So there are definitely some interesting challenges there, but I think it could be a really fruitful area for future research.
All right, so that's one possible direction. What else comes to mind?
Well, another thought I had is, what if we combined this local symmetry exploitation with other forms of structure exploitation? The paper mentions low-rank tensor decompositions as another way to create more compact representations.
Yeah, okay. So could we train an RL agent to somehow simultaneously leverage both local symmetries and low-rank properties of the tensors that it encounters during variable elimination?
Exactly. And that would probably require a much more sophisticated way for the RL agent to represent the state of the problem. It would need to be able to keep track of both the symmetries and the low rank structure.
Right. And the RL agent's cost function would need to be carefully designed so that it balances the potential benefits of exploiting those different types of structure.
Precisely. Now, to give you a concrete example of where this might be really useful, think about drug discovery.
Okay, drug discovery. That's a field where AI is already having a big impact.
It is. And probabilistic graphical models are being used to model things like the interactions between different parts of a molecule.
Okay, I can see how that would be useful for predicting how a drug might behave in the body.
Exactly. And within those models, you might have some parts of the molecule that exhibit these nice symmetrical relationships, while other parts might have interactions that are well approximated by low-rank representations.
So if you had an RL agent that could learn to exploit both of those types of structure, you could potentially make those drug discovery models much faster and more accurate.
Exactly. And that could lead to the development of new drugs and therapies much more quickly.
Wow, so the potential applications here are really exciting.
They are, and it's really just scratching the surface. I think there are a lot of other domains where this kind of approach could have a big impact.
All right, so to wrap things up, it sounds like this paper is making a really valuable contribution to the field of probabilistic inference. They're bringing together ideas from RL, tensor networks, and symmetry exploitation in a really clever way.
They are, and it's opening up some really promising avenues for future research.
Absolutely. If any of our listeners want to delve deeper into the technical details, we highly encourage them to check out the full paper, which we've linked to in the show notes.
And as we continue to explore these new approaches to efficient probabilistic inference, it really makes you wonder, what are the limits of what AI can achieve when it can reason about uncertainty not just effectively, but also really efficiently? That's a question that's going to keep me thinking for a while.
It is, and I think it's a question that should keep all of us in the AI community thinking. Because the more efficiently we can make these AI systems reason, the more we can unlock their potential to solve some of the world's most challenging problems.
Well said. And on that note, I think it's time to wrap up this deep dive. Until next time.
Until next time.